Welcome to Smart Physics as we complete our step-by-step walkthrough. In this video, we are journeying through the entire Cambridge IGCSE Physics Theory Component 41 of October-November 2025. We will solve each question step by step, and I will provide the common mistakes candidates made and the expectations from the markers. Let's delve into it. A train travels with a constant velocity of 56 meters per second on a horizontal track. The mass of the train is 440 kgs. I've underlined these three because they are key in solving this problem. We have the first physical quantity, which is 56 meters per second velocity. We have the second part, which is very important. It's horizontal track, meaning it's a linear motion. Therefore, we can employ equations of motion, very important in the other part of the question. And mass is the second physical quantity given, which is 440 kgs. Item A. So item A reads, state the difference between the velocity of the train and its speed. This question is coming straight from vectors and scalars, and we are supposed to know the difference between a vector and a scalar. We are also supposed to know that velocity is a vector and speed is a scalar. So the answer should be given as velocity is a vector, while speed is a scalar. Alternatively, you can talk of direction and lack of direction, since a vector has direction while a scalar doesn't. So you can actually say velocity has direction while speed has magnitude only. Speed is a scalar, so it doesn't have direction. It has magnitude only. But the key part of this question was to check if students understood that velocity is a vector while speed is a scalar. Let's quickly go to part B. Part B of the question says, calculate the kinetic energy stored in the moving train. The first thing I want you to understand is how to use the space provided, because there is a key instruction here which says write your answers in the space provided. You are not supposed to write on barcodes. Do not write on barcodes. Only write on spaces provided. Take note of these two important instructions. So you must be able to use your space in such a way that you don't end up writing on barcodes. So I'm going to divide my space like this. I call this my play area, and this is where I put my presentation. This helps me avoid writing on barcodes. Play area, that's where I extract data, try formulae, and then when I'm done, this is where I do my final presentation. So I'm going to extract data here. Calculate the kinetic energy stored in the moving train. We know that kinetic energy is the energy stored by a moving object, or energy for movement. So we are going to extract data relating to kinetic energy. We know that its speed is 56 meters per second. We know that its mass is 440,000 kgs. We are told to find kinetic energy, which I'll call question mark. Kinetic energy is question mark. By straight recalling from class or from notes, kinetic energy is equals to half the mass of an object times the square of its speed. By substitution, we're going to have half the mass 440,000 times the square of velocity 56 squared. If you use your calculator very well, you're supposed to find 690 million joules. Right on the space provided, I'll put it in scientific notation, 6.9 times 10 to the power 8 joules. two key areas where students lost marks. Put units. If you don't put units in this particular question, you can't get 2 out of 2. Number 2, a minimum of 2 significant figures for all answers from calculations. So my answer is in scientific notation, but to a minimum of 2 significant figures. So lots of students did not put units. If units are not given here, it means they are part of the answer. You should present them to demonstrate that you know the units. Number 2, you should note that all your answers are required to a minimum of 2 significant figures unless the question says so. So take note of these 2 things. These are areas where students drop marks. So let's quickly now go to part C of the same question. Part C says the train has a uniform deceleration of 1.2. Calculate the constant braking force which brings the train to rest. So we are given acceleration of the train is minus 1.2 meters per square second. Where is the negative coming from? We know that deceleration is negative acceleration. So I will need this in my calculations. And they are saying find the braking force. So they want us to find the force, which is a question mark. For us to find a force, we are going to recall on Newton's second law, which says the net force acting on an object is equals to its mass times its acceleration. What is the mass? 440,000 kgs times the acceleration negative 1.2 meters per square second. With this, we are going to get 528,000 newtons, which are negative. Negative implies it's retarding force. So here we are interested in the magnitude of that force. So we can safely put it in scientific notation, 5.3 times 10 to the power 5 newtons. 2 important areas where you may lose marks: units. Units are not given here, so we need to put units, and 2 significant figures. My answer has the proper unit, the Newton, and it's to a minimum of 2 significant figures, 5.3 times 10 to the power 5 newtons. So it can score these 2 marks. Take note of that. Let's go to part B. Part B says calculate the distance traveled by the train as it comes to rest. There are 2 ways to deal with this particular question. We can use the work energy theorem. We can use the work energy theorem, or we can use equations of motion. These 2 can be used to take us to the answer. Let me start with the work energy theorem, then I'll go to the alternative equations of motion. Now, the work energy theorem says energy transferred is equals to work done, but work done is also equal to force times distance. The energy transferred by an object is equivalent to the work done, because energy is the ability of work. When that energy is being transferred, work is being done. And we know that work is the product of force and distance moved by the force along the line of action of the force. So in this case, the train had kinetic energy. How much kinetic energy? 690 million joules of kinetic energy. And it did some work. So we can actually say the kinetic energy which was lost in the braking process is equivalent to the force that caused the braking times the distance moved in braking. And we want to make distance subject to formula. We divide both sides by F, we end up having distance is equals to kinetic energy lost over the force which was causing braking. With this, we can now safely do our substitution and say distance traveled is equals to 6.9 times 10 to the power 8 joules. Kinetic energy lost was equivalent to this, and the force causing braking, we are just from calculating it over here, which is 5.3 times 10 to the power 5. So we can safely say divided by the force, which is 5.3 times 10 to the power 5 newtons. When this is done, we are going to find 1306.8 meters, and in scientific notation this is 1.3 times 10 to the power 3 meters. If you want, you can use kilometers. 1.3 kilometers. This answer will be correct, this answer will be correct, as long as the unit is consistent. So this is method number 1 by the work energy theorem. Or alternatively, we can use equations of motion. We know that v squared is equals to u squared plus 2ax. Now looking at this, we know that it's coming to rest. Therefore, the final velocity is going to be 0. So we can actually say negative u squared is equals to negative 2ax. Let's talk about the negatives. Where is this negative coming from? We moved u to the left side of the equal sign. So it was positive, it becomes negative. Where is this negative coming from? Our acceleration is retardation. It's a braking force. So we know that retardation is negative acceleration. So we have a negative from negative acceleration, retardation, and negative by moving u squared to the other side. We are looking for x. We need to divide both sides by minus 2a. We end up having our x is equals to u squared over 2a. By substitution, this is going to be 56 squared over, what is 2a? 2 times 1.2. If you punch your calculator very well, you are supposed to get 1301.9 meters. So our distance using kinematics is 1301. By using scientific notation, we have 1.3 times 10 to the power 3 meters, which is the same as 1.3 kilometers. So you write whichever you want over here, and you see by work energy theorem we're finding 1.3 kilometers. By kinematics we're still finding 1.3 kilometers. Key areas where students lose marks: you are supposed to put units, either meters or kilometers, and you're also supposed to have a minimum of 2 significant figures. With this, you score all the marks. Question number 2. Table 2.1 contains information about the planet Mars. Mass of Mars 6.4 times 10 to the power 23 kgs. Gravitational field strength at its surface 3.7 newtons per kg, and average density is 3,900 kilograms per cubic meter. Define gravitational field strength. Gravitational field strength is what we normally just refer to as a small g. For us to define gravitational field strength effectively, we should recall that weight is equals to mass times gravitational field strength. Since we want to define gravitational field strength, we need to make gravitational field strength subject to formula. So I'm going to divide both sides by m, and we remain with G is equals to W over m. You should recall that weight is a force, so similarly we can say this is force over m. Now to define gravitational field strength, we navigate from this mathematical formula. G is equals to force divided by mass, and we put this expression in words, which says gravitational field strength is the force per unit mass in a gravitational field. So the expected answer was gravitational field strength is the force per unit mass on an object in a gravitational field. With this, you earn your mark. B, item 1. An object has a weight of 42 newtons at the surface of the earth. Calculate the weight of the object at the surface of Mars. Now, this question required students to recall that mass does not change from place to place, mass is constant irrespective of places. So the mass on Earth is equals to the mass on the surface of Mars. So we needed to use the data provided for the surface of Earth to find the mass on Earth. Once we find the mass on Earth, we use that mass to find the weight on Mars. Now, key things to remember: gravitational field strength on Earth is 9.8 newtons per kg. This you should always know. You are required to know this. In an exam situation, if you happen to forget, what do? You go to the instructions, the cover page, you find it given over there. So let's use the equation for weight, mass, and gravity to find the mass of the object on Earth. We know that weight is mass times gravity. Then we change the subject because we're looking for mass. By changing the subject, we have mass is equals to weight divided by gravity. The next thing is substitution. We know that the weight is 42 and gravity is 9.8. We do substitution for us to find our mass of the object to be 4.29. With this done, we can now recall the equation for weight again. We know that weight is mass times gravity. So where do we get the mass? The mass of an object on Earth is equal to the mass of an object on Mars. So this is the mass we are going to recall here and say, since mass on Earth is equal to mass on Mars, the 4.29 kg is the mass of the object wherever it is. So we do our substitution. 4.29 times gravitational field strength of Mars, which is given on the table as 3.7, and we get our 15.87 newtons. Two important things before you present your final answer in the space provided. If the units are not given here, you are required to put units. So your final answer must have units. Number one, units. Number two, our answers should be to a minimum of 2 significant figures in our presentation. So the ideal answer will be 16 newtons. A minimum of 2 significant figures with units. If any of these is wrong, then the answer, you cannot get the answer mark. Part 2 of B, calculate the volume of mass. For us to find the volume, we need to recall the equation for mass, density, and volume. And let's extract data and see what we were given in the table. So in the table, we are given the mass of Mars and we are given the density of Mars. With this, we should know that density is mass per unit volume, which is mass divided by volume. We are looking for volume. Let's change the subject. We are going to say volume is mass divided by density. Straight substitution, and we find 1.6 times 10 to the power 20 cubic meters. Don't forget always these two rules. Units, if not given, my unit is there. A minimum of 2 significant figures. A minimum of 2 significant figures. With this, you earn all the marks. Part C reads, Fig 2.1 shows a space buggy that is tested on Earth. So the experiment is happening on Earth. The buggy is traveling at a constant speed in a straight line. This is very important information. If you like highlighting, this part should be the one you highlight. It's very important because speed in a straight line is velocity. Speed in a straight line is velocity. In other words, we can actually say it's moving at a constant velocity. The driving force is 30 newtons. So the driving force is 30 newtons. Item 1. Draw and label one arrow on Fig 2.1 to show the size and direction of the resistive forces on the buggy. Now, since they said it's traveling at a constant speed in a straight line, velocity is constant. And if velocity is constant, acceleration is 0. Velocity is constant. If velocity is constant, acceleration is zero, because acceleration is the rate of change of velocity. Since velocity is constant, the velocity is not changing, so the rate of change of velocity is zero, meaning acceleration is zero. And according to Newton's second law, if acceleration is zero, the net force is also zero. And if the net force is zero, the driving force and the resistive forces are balanced. In other words, the force going backwards is also 30 newtons. So that if we say 30 driving force minus 30 opposing force, we're going to get a net force of zero, which gives us an acceleration of zero. Hence, we say the object is in dynamic equilibrium. Dynamic equilibrium. It's moving, but it's at equilibrium. It's in dynamic equilibrium. The resistive force balances the driving force, meaning it will maintain the same velocity since there is no acceleration. With this, that's how you earn your 2 marks. Direction and magnitude. Direction is opposing, magnitude is equal. How do we know there is no acceleration? How do we know velocity is constant? Therefore, there is no net force. Part 2 of C. Air resistance on Mars is less than air resistance on Earth. The same driving force is exerted on the buggy on Mars. State the effect this has on the resultant force on the buggy on Mars. Let me draw something here to illustrate what's happening. So I'll start with the situation on Earth. On Earth, this is on Earth, the buggy is under the influence of a driving force of 30 newtons. And we said the resistive force is also 30 newtons. So that F net is equals to 30 newtons minus 30 newtons, which is equals to 0. Now, let's go to Mars. We expose it to the same driving force of 30 newtons, but the air resistance becomes less, meaning the opposing force is less. For argument's sake, I'm going to say it's 20 newtons, for argument's sake. So what will be the net force in this particular case? So the net force will be 30 newtons driving force minus 20 newtons opposing force to give us 10 newtons. So on Earth, the net force is 0. On Mars, the net force is bigger than 0. So the net force on Mars is greater than the net force on Earth. In other words, we can actually say the effect causes the net force or the resultant force to increase. So the ideal answer was the resultant force increases or it becomes greater. State the relationship between the resistive forces, driving forces, and opposing forces. Since they are opposing each other, we are going to allocate one positive, one negative. Therefore, the resultant force is equal to driving force minus resistive force. This is the particular relationship. Question number 3. Fig 3.1 shows a simplified diagram of a solar cell. Item A, describe the energy transfer in the solar cell. If you look at it carefully, you will see that the input is light. So light energy is the input and the output is electrical energy. Our output is electrical energy. Our output is electrical energy. Our output is electrical energy. Therefore, if we are to describe the energy transfer in the solar cell, we need to talk about the energy conversions in a description format, not stating. So we are going to have an ideal answer which says light energy from the sun is transferred into electrical energy in the solar cell. Part B of the same question suggests how black coating allows the solar cell to transfer more energy. Now, the interesting thing is you should know the properties of black color in terms of energy absorption and reflection. So black, it's a good absorber because it reflects less energy. So the ideal answer should be the black coating absorbs more light and reflects less. The black coat absorbs more light since it's less reflective when it comes to energy. So more light energy is available to be converted to electrical energy. With this, I will proceed to part C. Part C reads 0.72 kilowatts of light is incident on a solar cell in Fig 3.1. The cell has an efficiency of 75%. Item 1, calculate the output power of the cell. So I prefer selecting data, then we do the selection of the right equation. So what are we given? We are given input power 0.72 kilowatts and we're given the efficiency as 75%. I always prefer reducing my efficiency to decimal because it makes the equation easier to deal with. With this data, we can now record the equation for efficiency, which says efficiency is useful output power divided by input power. Our useful output power is the requirement of the question, hence we need to change the subject. Let's change the subject and make output power subject of formula. We will have output power is efficiency times input power. Once we reach this stage, the next thing is a quick substitution. 0.75, that's our efficiency, times 0.72, that's our input power, getting 0.54 kilowatts. Take note, the units are not given, so your answer is never complete without units. Number 2, I've presented my answer to a minimum of 2 significant figures. Avoid answers like 0.5. You round off to 1 significant figure. With this, the answer mark, you will lose it. Avoid 1 significant figure. All answers are supposed to be a minimum of 2 significant figures with an appropriate unit. Part 2 of C, state the meaning of the term kilowatt hour. Now, I want you to understand that kilowatt hour is energy. Kilowatt hour is energy. Remember, energy is equals to power times time. Now, kilowatt times hour will give us kilowatt hour. In other words, we have kilowatt, which is power, times time in hours, which is energy. So a kilowatt hour is a unit of energy. So what is a kilowatt hour? When a gadget of power rating 1 kilowatt runs for an hour, the energy consumed is a kilowatt hour. So the ideal answer for this particular question was a kilowatt hour is the amount of energy used or transferred when electrical power of 1 kilowatt is used for an hour. Right, with this we can quickly go to item number 3 of C. Item number 3 reads, energy is produced by each solar cell. So this is each solar cell. We need to underline this part because we use it. Each solar cell. Each solar cell. For an average of 6 hours per day. So each solar cell runs for an average of 6 hours per day. It doesn't run 24 hours, but 6 hours each day. A household uses approximately 7,400 kilowatts hour of electrical energy per year. So energy requirement per year is 7,400 kilowatts hour. Calculate the number of solar cells needed to produce energy for one household. Here we are given information about one solar cell, how much time it runs a day, and how much energy is required. So the first thing is we need to find energy produced by each cell per day. We go to energy produced by each cell per year. Then if we divide the energy requirement per year by the energy which is being produced per year, we find the cells required. So energy is power times time. For us to find energy in a day, we say power times time in a day. So each cell is rated 0.54 times 6 hours in a day, mounting up to 3.24 kilowatts hour per day. We take this to 365 days in a year. So we now have energy per year is 3.24 times 365, which is going to give us 1182.6 kilowatt hour. This is energy per year. Now that we know the energy per year and the energy requirement per year, we can safely say number of cells is equal to energy required per year divided by the energy produced by each cell per year. Therefore, it requires 6.26 cells. It requires 6.26 cells to produce this energy in a year. But there is a very important aspect of the question said your answer must be as a whole number of solar cells. So should we pick 6 or 7? If we pick 6, they won't be producing 6.26. It will be less than 6.26. This fraction, where will it come from? This fraction, where will it come from? So we need to move to the next whole number, which is 7. 7 are the ones which can at least produce a minimum of this. So our final answer is supposed to be 7 cells. Question number 4. A 12 volts 50 watts immersion heater is used to heat 0.15 kgs of water in a beaker. The water is initially at room temperature of 20 degrees Celsius. The heat capacity of water is 4,200 joules per kg degrees Celsius. Calculate the energy supplied to raise the temperature of water from 20 degrees Celsius to 58 degrees Celsius. This question is coming from thermal properties, specifically specific heat capacity in thermal physics. When you are dealing with such questions, it's very expedient for you to extract data first. There are too many data factors in the question, so extracting them will make it easy for us to choose the right equation. So what are we given in the question? We are told that the mass is 0.15 kg. We are told that the initial temperature is 20 degrees Celsius and the final temperature is 58 degrees Celsius. Hence, with this, we can find the change in temperature. Always remember that change in temperature is equals to final temperature minus initial temperature. So final temperature 58 minus initial temperature 20, giving us a change in temperature of 38. Specific capacity is given as 4,200 joules per kg degree Celsius. Let's recall the equation for specific capacity, mass and energy. It will be energy required is equals to mass times specific capacity times change in temperature. By substitution, 0.15 is the mass, 4,200 is the specific capacity, and delta T, the temperature change, is 38, giving us 23,940. Now, do not leave this as your final answer, otherwise you get 2 out of 3. Remember the key rules in your presentation of the final answer on the spaces provided. If this is not provided, the unit is not provided, you are supposed to provide your final answer with the unit, which is a joule. If you leave it without a unit, you won't get the answer mark. The next thing is it must be to a minimum of 2 significant figures, of which you can escape here because it's already more than 2 significant figures. So my final answer will be 24,000 joules. The appropriate unit was presented and the answer is to a minimum of 2 significant figures. Let's move on to part B. Part B reads, the immersion heater is removed from the beaker. One metal rod and one plastic rod are placed in the beaker of hot water as shown in Fig 4.1. Let's analyze Fig 4.1. It is point X, which is the same point as X on the other rod. Why? Point X is 2 centimeters from the end of the rod. In other words, it's 2 centimeters here, it's also 2 centimeters here. So point X is the same point from the bottom to X. What's happening on the plastic is what's happening. Describe how the temperature of X on each rod changes after the rods are placed in the beaker. Explain your answer. So the beaker has water at 58 degrees Celsius. but the rods are at 20 degrees Celsius. So temperature must be increasing from 20 degrees Celsius going high at point X. But how is energy moving from the bottom? It's going to be moving by conduction since these are solids. Now, we should know by now that metals are good thermal conductors, while plastics are poor thermal conductors. With this in mind, we expect heat to reach X faster on the metal rod than this side. But why is it that we're saying heat will reach this point faster before this point? Let's look at the mechanism of conduction. Conduction moves through, number one, lattice vibrations. Lattice vibrations. In other words, heat is moving from point to point through vibrations of particles. So this happens in metals as well as in plastics. So here we have lattice vibrations. Right. After this, we have mechanism number two, which is called electron drift. Electron drift or movement. So heat can move by electron movement. We know that metals are lattice of positive ions in a sea of delocalized electrons. A metal is a lattice of positive ions in a sea of delocalized electrons. So when these electrons move, they heat up. As they are moving, they bump into the lattice of the atoms, which transfers heat at the point of collision. And this can only happen with metals, but here we don't have metal electron drift, no delocalized electrons, no delocalized electrons. So here electron drift does not happen. So in metals, heat is going to move by lattice vibration and by electron drift. Here it's only going to move by lattice vibrations. So we expect heat to reach this faster because metals are better conductors since they have two mechanisms through which heat moves. So what could be the ideal answer? The ideal answer is point X on the metal rod heats up more quickly than point X on the plastic rod. This is 1 mark already. I've taken out 1 mark out of these 4. Because metals transfer thermal energy by conduction. This is method mark number 2. Because I've identified that heat will be moving by conduction. And it's faster in metals than in plastic. So this is method mark number 3. So just this paragraph, I've raked 3 marks out of 4. Where does the 4th mark come from? I need to justify this statement where I said metals transfer thermal energy by conduction faster than plastics. Why is it so? Now I'm comparing. Here they use lattice vibration and electron drift, while nanometals only use lattice vibrations. So that will be in my concluding statement. The metal conducts thermal energy as delocalized electrons in the metal move. There are no delocalized electrons in plastic. This is my 4th mark, giving me a total of 4 marks. Question number 5. A dolphin communicates with other dolphins underwater by emitting sound of frequency 7 to 15 kilohertz. Item A. State the value of the speed of sound in air and state how the speed of sound in water differs from the speed of sound in air. So you should know the range of sound in solids, liquids, and gases, of which air is a gas. So in gases, sound is expected to be between 330 meters per second and 350 meters per second. So I'll pick any value within this range and represent the speed of sound in air, since air is a gas. Now, for us to compare the speed of sound in water, how it differs from the speed of sound in air, we need also the range for the speed of sound in liquids. So the speed of sound in liquids ranges from 1480 meters per second to 1530 meters per second. With this, we can safely see that the speed of sound in air is less than the speed of sound in water. So we can safely say the speed of sound in water is higher, or it's faster than the speed of sound in air. That's how you get 1 mark if both are correct. Part B, start and explain if humans with normal hearing can hear all the sounds emitted by the dolphin. Now, for you to answer this question effectively, you need to know that audible range ranges from 20 Hz to 20 kilohertz. With this, you now compare the frequency of 7 kilohertz to 15 kilohertz. With this, we can safely see that the dolphin sounds all fall in the audible frequencies. So we can safely say yes, a normal human being will hear the sound. And how do we explain? The normal hearing ranges from 20 Hz to 20 kilohertz, of which all the dolphin sounds lie in this range. With this, we get 2 out of 2. Let's quickly move to part C. Part C reads, complete table 5.1 to describe the differences in loudness and pitch of 2 different dolphins. So there are 2 different dolphins. One is producing sounds of frequency 14 kilohertz with a very large amplitude, while the other one is producing 8 kilohertz with a small amplitude. For us to complete this table on loudness, we need to understand the relationship between loudness and amplitude. Amplitude of sound is its loudness. Amplitude of sound is its loudness. How are they related? Let me illustrate it over here. They are directly proportional. As the amplitude, A for amplitude, is getting smaller, the loudness is reducing. L for loudness is also getting smaller. They are directly proportional. The bigger the amplitude, the louder the note. So we can complete this part. Since this one has a larger amplitude, it's louder than this one with a smaller amplitude. So this part, we quickly say larger amplitude, louder, smaller amplitude, quieter or less loud. Then the next thing is to deal with pitch. Pitch of sound is its frequency. Pitch of sound is its frequency. So we need to understand the relationship between pitch and frequency. They are also directly proportional. As F for frequency gets smaller, P for pitch also gets smaller. As F for frequency gets smaller, P for pitch gets smaller. So this one has higher frequency indicating higher pitch, lower frequency indicating lower pitch. So we complete that part. This one, for higher frequency, it will give us a higher pitch. For lower frequency, it will give us a lower pitch. With this, we harvest these 2 marks. Part D. Complete the sentence to describe how sound is transmitted through water. Sound waves are made of vibrating particles. Why? Sound, we introduce vibrations to a medium to produce sound. A medium, it's anything with particles, with matter. So the sound waves are made of vibrating particles which produce compressions and rarefactions. A compression is a region of high pressure, and a rarefaction is a region of low pressure. Remember, a compression is defined as a region of high pressure where particles are closer together than normal, and a rarefaction is defined as a region of low pressure where particles are further apart than normal. The sound wave travel parallel to the direction of vibrations. Sound is a longitudinal wave, so the vibrations and the direction of propagation, they are parallel to each other. In other words, when the source is vibrating left to right, sound is moving along the same plane. So the vibration and the propagation are in the same direction. Vibrations are lateral vibrations, while propagation is parallel. This is a longitudinal wave. Question number 6. Fig 6.1 shows part of an optical fiber used in high-speed broadband communication. Item A, state 2 advantages of using optical fibers in high-speed data transmission compared to electrical signals sent on copper wires. You should have 3 to 5 advantages which were shared by your teacher or your coach in class. So I will just share with you the first 2. I've ranked them according to my own weighting. So the first 2 we should know. Number 1, optical fibers, they carry or transmit higher data more data at very high speeds. So there is high rates of data transmission. They are faster in data transmission because they use electromagnetic waves which move at very, very high speeds, so they can transfer data at very high rates or high speeds. Number 2, optical fibers do not suffer from electrical interference. There is no interference in the fiber because the core is protected by the cladding, and it's TIR throughout the fiber, so we're not going to have interference. And number 3, I'm going to say we have secure data. We don't have data losses. Since it moves through total internal reflection, we expect the data in to be the data out, because all the data will keep reflecting until it reaches the other end. Now the other 2 which I can add for you, they carry large amounts of data and information. They can carry so much data and information. And also, since they are from glass is transparent to infrared, which is used in optical data transmission. Right, let's quickly go to part B. Part B says the optical fiber is made of glass with a refractive index of 1.4. Calculate the critical angle C. Now, for us to calculate this, we need to recall the 3 equations which were given in class from this particular topic. We defined the refractive index as the ratio of the sine of angle of incidence to sine of angle of refraction. This is the first equation we received in class. We were also defining refractive index as the ratio of the speed of light in a vacuum to speed of light in any medium, and we called this equation number 2. Then finally, under total internal reflection, we said refractive index is 1 over sine the critical angle. This is equation number 3. So one of these equations is going to be suitable for us to solve this problem. But for us to come to that point, let's extract data and see what we were given. So we were given the refractive index n, and we were required to find the critical angle. So we can safely say the critical angle is equals to question mark. With this in mind, there is only one equation which has n and a critical angle. So the suitable equation for this particular problem is equation number 3. So we will recall equation number 3. and say n is equal to 1 over sine c. Once this is done, we want to make sine c such a formula, so that consequently we make c such a formula. So we should know that sine c is equal to 1 over n, and for us to find the angle, we recall this inverse of the sine function. With this done, the next thing is substitution. The sine inverse of 1 over n, our n is 1.4, we're going to get 46. At this point, never submit your answer like this, because it lacks the unit, so it cannot score all the marks. So the final answer must be presented together with the unit for these 3 marks to be harvested. Now, part 2 says, state the meaning of critical angle. For us to define critical angle, I will take you back to total internal reflection, and I have my normal here, and this is air, this is water. So I have light moving from water towards air. So critical angle is the angle of incidence for which the angle of refraction is 90 degrees, for which the angle of refraction is 90 degrees, for which the refracted ray lies parallel to the principal arc, to the boundary. So quickly let's define the critical angle. The angle of incidence for which the angle of refraction is 90 degrees. With this, we say we've harvested that mark. Item 3 of B. On fig 6.1, label the angle of incidence. They want us to label the angle of incidence on fig 6.1 of the ray of light as it hits the wall of the glass fiber. Draw the continuation of the ray until it leaves the glass fiber. So there are 2 parts: putting a label for the angle of incidence and drawing the continuation. So we are going to revisit the diagram. For us to draw the angle of incidence, we need the normal, because the angle of incidence is the angle between the normal and the incident ray at the point of incidence. So we bring in the normal at the point of incidence, and the angle between the normal and the incident ray is the angle of incidence. So this is the angle we are talking about. The angle between the incident ray and the normal at the point of incidence is the angle of incidence. We move on to part 2. We want the continuation of the ray until it leaves. How does the ray continue? TIR, total internal reflection, will be taking place according to the laws of reflection. In other words, at every point of incidence, the angle of incidence must be equal to the angle of reflection. So by eye observation, the marker should see that the angle of incidence is equal to the angle of refraction until it comes out. This is by eye observation. With this, we would have wrecked all the 2 marks. Question number 7 reads, Fig 7.1 shows a circuit containing 6.0 volt battery of cells and 3 identical resistors. It's very important to note that the resistors are identical, meaning they have the same resistance. Resistance R1 is equals to resistance R2, which is equals to resistance R3. Now item A says switch 1 is closed and switch 2 is open. The current in the ammeter is 0.080 amps. Calculate the resistance of R1. Now if switch 2 is open, it means we only have one loop in this circuit. So current will only flow around this loop. No current will come to this loop since this one is open. Meaning the total resistance in this circuit is the same as R1 plus R2, because R3 has been taken out since switch S2 is open. So for us to find the resistance of R1, we need to first record the data given. So we are given that the voltage in the circuit is 6.0 volts, the current is 0.080, and by Ohm's law we can find the total resistance, because Ohm's law says total resistance is total voltage divided by total current. So our total voltage as given, it's 6 volts, and our total current is 0.08, giving us a total of 75 ohms in the branch. So in other words, we can safely say resistance R1 plus resistance R2 is equals to 75 ohms, right? So since the resistors are identical and they are in series, the sum of their resistance is equal to 75. Therefore, we can say R1 plus R2 is equal to 75. Since they are equal, we double R1. We are going to find 75 divided by 2 is equal to 37.8. Every time when you are presenting your final answer in the space provided, ensure that your answer is to a minimum of 2 significant figures. So my final presentation is going to be R is 38 ohms. Key notes: if you are not given units, ensure to put units. So we have put units, ohms. My presentation, the final answer is to a minimum of 2 significant figures. Hence, I can harvest both these marks. Part B reads, S1 and S2 are both closed. Determine the reading on the ammeter. Show your working. So let me recall the circuit. We are now saying S2 is closed, meaning we now have 2 loops. The upper loop where current is flowing, and the lower loop where also current is flowing. We now have 2 loops, branch 1 and branch 2. So current comes, it reaches this junction. It's called a node or a junction. Then it divides. Part of it goes to the upper branch, part of it goes to the lower branch. Now, for us to determine the reading of the ammeter is reading the total current, because it's current before division. There are 2 important things we need to recall. Number 1, parallel circuits are current dividers. In other words, the total current passing through the ammeter will divide into branch 1, so we have current 1, and branch 2, so we have current 2. So we can safely say total current is equal to current through branch 1 plus current through branch 2. That's the first thing we need to note. The second thing we need to note is voltage is not divided in parallel. In other words, the voltage of the source is equal to the voltage of this branch, which is 6 volts, and the voltage of this branch also, which is 6 volts, because voltage is not divided. Therefore, we can safely say the voltage applied in branch 1 is equal to the voltage applied in branch 2. So with this, let's start by finding the current passing through the top branch. The top branch has a resistance of 75 ohms, because this one is 37.5, this one is 37.5. We add the 2, we get 75. Now, according to Ohm's law, V over R is equals to I. What is V? We said this branch has 6 volts. What is R? It has a total resistance of 75 due to the combination of these 2 resistors in series, giving us a current of 0.08. So we can safely say current 1 in the branch 1 is 0.08 plus. Now current in branch 2 has a voltage of 6 volts, and there is only one resistor of 37.5, and we're going to get the current in branch 2 to be 0.16. So if we want the total current which is being read by the ammeter, we add the 2 currents, 0.16 bottom branch plus 0.08 top branch we are going to get 0.24 amps. So all the working is shown, the current divider rule at the junction, and the voltage is being applied equally across all branches. Part 2 of beam. Explain in terms of work done and potential difference why there is a large heating effect in R3 than in R1. Let's erase this so that we can address this question with a clear picture. Right. So we want to explain in terms of work done and the potential difference why there is a larger heating effect on R3 than R1. Now, the first thing we need to understand here is the branch voltage are the same. We have 6 volts here and 6 volts here because we want to explain in terms of voltage and work done. So these 6 voltages within branch 1, they are divided in such a way that R1 takes 3 volts and R2 takes 3 volts, since these resistors are identical. So in this branch we have 6 volts, but 3 volts are applied across R1 and the other 3 volts are applied across R2. In this branch we have 6 volts as well, but all of them are applied across R3. So R3 has a higher voltage applied across it. Since it's a single resistor in the branch, it's not sharing it with another resistor. Now, voltage is the energy per unit charge. In other words, voltage is work done per unit charge in passing through that charge across a component. Across R1, there is a 3 volt, meaning less energy is being dissipated in moving a coulomb of charge across R1. So the ideal answer was R3 is in its own branch, so the full 6 volts acts across it. The full 6 volts are applied across it. The voltage is shared between R1 and R2, so the potential difference across R1 is smaller. It's 3 volts, which is smaller than 6. Since work done depends on potential difference, the work done, energy transferred per unit charge, per coulomb of charge, depends on potential difference, which is the work done. More work is being done in moving a coulomb of charge across R3. Therefore, there is a larger heating effect in R3. Question number 8 reads, Fig 8.1 shows a solenoid. Draw on Fig 8.1 4 complete magnetic field lines to show the pattern and direction of the magnetic field inside and outside the solenoid. And it's a 4 marker. There is a lot of work here. Now, for us to draw the direction of the magnetic field lines, we need to identify the North Pole, because the direction of the magnetic field is defined by the North Pole. And since we're dealing with the magnetic field surrounding a solenoid, we need to record the right-hand grip rule for solenoids. So let me quickly record the right-hand grip rule for solenoids over here. The right-hand grip rule for solenoid says, when the right hand grips a solenoid in such a way that the 4 fingers curl in the direction of the current, then the thumb will point to the North Pole. So let's superimpose the right hand grip rule over our solenoid. We follow a conventional direction of current from positive to negative. So this is how our current is flowing in the solenoid, over and under on the other side. So let's superimpose. Our current is going over and under on the other side, yet our thumb is pointing to the left. Therefore, our North Pole is on the left and South Pole on the right, like this. With the North Pole determined, we can now complete the magnetic field lines. The field lines are expected to come out of the north and enter in through the south like this. They come out of the north and they enter in through the south, like this. Now the question says inside and outside, the pattern and direction. So the pattern, we have inside where they are parallel, coming out of the north and entering in through the south, and outside where they are circular or elliptical, coming out of the north and entering in through the south. So inside they are parallel from the north to the south, outside they are elliptical or circular from the north to the south. So we have dealt with direction north to south, pattern inside parallel, outside circular. So with this we have completed these 4 marks. Part 2 says, mark a point inside the box in Fig 8.1 where the magnetic field is strong. Label this point B. So B was expected to be somewhere here. Why? The field is stronger where there is a high field density, where we have more field lines per unit area. If we put a square here, we are going to capture most of the field lines. If we put a square of the same size here, we are only capturing 2 field lines. Hence, we have more field lines per unit area inside the solenoid than outside the solenoid. Hence, the field is stronger inside the solenoid. So your explanation was the field lines are closest together at point B, showing that the magnetic field is strongest over there. Let's move on to part B. Part B says, Fig 8.2 shows a solenoid in an electric circuit for a bell. B item 1, complete the circuit in Fig 8.2 with a symbol for a direct current power supply. Now, in your syllabus, you are given a chart with circuit symbols that are expected to be known by you. A direct current as a positive and a negative terminal like this. And you were supposed to complete it over this gap which was given in this circuit. So you were expected to complete a direct circuit power supply like this. With this, you can tick your 1 mark in the bag. Part 2 says, explain why the soft iron arm pivots, making the striker hit the bell when the switch is closed. Let me recall the circuit so that I explain it better. We now have our power supply. And the switch has been closed, meaning current can now flow through the circuit. So the flow of current energizes the electromagnet. So we say the electromagnet is energized. What do we mean by that? The iron bar inside the magnet begins to behave like a magnet. So we now have a magnet here. Because it's a magnet, soft iron is electromagnetic. It's attracted to a magnet. So it will be pulled towards the magnet. It's attracted to the magnet like this. In so doing, it moves with the striker, which is going to hit the gong. So the ideal answer was, when the switch is closed, the solenoid becomes an electromagnet. It becomes energized. And attracts the soft iron arm, and the soft iron arm pivots. Part B says, explain why the arm pivots back to its original position after the striker hits the bell. So when the striker comes in contact with the bell here, it creates a separation, because as this moves down with the striker, there will be a separation over the contacts here. So here we have a separation. In other words, the contacts are no longer in contact. Hence, there is an open switch here. The current stops flowing, the electromagnet loses its magnetism, and this attraction disappears. Hence, the spring metal will pull back the soft iron arm, causing it to move backwards. So the ideal answer was, after hitting the bell, the contacts are broken, the switch opens again, cutting the power to the solenoid. The soft iron arm is pulled back by the springy metal, making it pivot back. With this, you take these 2 marks and consequently 10 marks. Question number 9, I'll read. Describe the structure of an atom of helium-4, mass number 4 and atomic number 2. So you are required to know that helium-4, atomic number 2, like any other atom, consists of a nucleus which has 2 protons and 2 neutrons. Outside the nucleus, we have 1 energy level or orbit, where 2 electrons orbit around the nucleus. So the ideal answer expected of you was a helium-4 atom has a nucleus. So identifying the nucleus, it's method mark 1, containing the constituencies 2 protons and 2 neutrons. This is method mark 1. It has a nucleus and its constituencies protons and neutrons. 2 electrons orbit around the nucleus in a single shell. The number of electrons is equal to number of protons, so this becomes method mark 1 to give us a total of 1, 2, 3. Now we have 3 out of 3. We mentioned the nucleus, its constituencies, and the number of electrons and their location. Part B says the sun is a medium-sized star powered by nuclear fusion reactions which release energy. State what happens during nuclear fusion reactions which form helium. Now, in thermonuclear fusion, which you talked about, you said 4 protons or hydrogen nuclei will combine to form a helium nucleus with a mass of 4 and atomic number of 2, releasing energy in form of gamma radiation. So the ideal answer was, during nuclear fusion reactions, 4 hydrogen nuclei fuse together to form helium nucleus, releasing a large amount of energy in form of gamma rays. Then you secure these 2 marks. Part 9b2 says, state 2 regions of the electromagnetic spectrum by which the sun radiates most of its energy. There are 3 major regions, so you just needed to pick the 2 from the 3 major regions. You can pick visible light, you can pick ultraviolet, and there are 3 including infrared. All hot objects emit infrared, so you could have picked the infrared, you could have picked the visible light, you could have picked the UV, and you secure the 2 points. Part C, describe what happens to a star when most of its fuel in the center has been converted to helium. So as thermonuclear fusion is happening, remember we said the hydrogen is being converted to helium. What will happen when it runs out of the fuel, the hydrogen, which is the fuel? So the first thing you need to understand is, when most of the hydrogen in the core is converted to helium, the star expands and cools. The star expands and cools, and it becomes. Now we have 2 cases. We have 2 cases. So you need to know which case. We have small to medium stars. So case 1 is small to medium stars, and case 2 is massive stars. These have different fates. Small to medium stars, they have their own fate. Massive stars have their own fate. But for both cases, when the hydrogen runs out, they expand and cool. Then small to medium stars, they form red giant. So this is mark number 1. Then this is mark number 2 for those who decided to go the small to medium stars. If you want to talk about massive stars, you say they form red supergiants. You don't need both of them, since there are just 2 marks. So 1 mark comes from talking about its expansion and cooling. The second mark talks about its later stage, whether a red giant for small to medium stars or a red supergiant for massive stars. With this, we would have secured the 9 marks from question number 9. Fig 10.1 shows the orbit of the Earth and the orbit of a comet around the Sun. Item A, state which orbit A or B is the orbit for the comet. Explain your answer. Now, the orbit was supposed to be selected as B. How do we get to this part? All orbits are elliptical, but comets, they are characterized by extremely elliptical orbits. All orbits are elliptical, but comets are characterized by extremely elliptical orbit. So this is our Sun. There is one end with a very big radius from the Sun, and there is one end with a very small radius from the Sun. That's what we mean by they are elliptical. If you look at orbit A, it's almost a sphere, a circle. The Sun, though it's not central, but it's almost a circle. But for comets, their orbits are highly elliptical. So that was supposed to be the explanation. A comet is a highly elliptical orbit. Part B says, describe and explain how the motion of the comet changes as it moves around the Sun. Now, the motion changes due to the shape of the orbit. 2 important things I want to talk about. When the comet is at point A, it's very far from the Sun. And when the comet is at B, it's nearer to the Sun. Therefore, here there is a stronger gravitational pull which causes it to move faster. Here there is a weaker gravitational pull, hence it moves slowly. That's the first thing. So you were expected to say the comet speed up as it moves closer to the Sun. So closer to the Sun, it's faster. It speeds up and slows down as it moves away from the Sun. This is just 1 mark. They are not 2. Because the question is in 2 dimensions, describe and explain. I have described. The comet speeds up as it moves closer to the Sun and slows down as it moves away from the Sun. I have 1 out of 2. Explain. Now I'm saying this is due to gravitational pull of the Sun, which is stronger when the comet is near the Sun. So when the comet is near the Sun, it experiences a stronger gravitational pull, causing it to move faster. And when it's far, it experiences a weaker gravitational pull because the separation is too big, which makes it move slowly. Or you can talk of energy conversions. Now, when we are far, let's talk of energy conversions. When we are far at A, the height from the Sun is very big. So it has very high gravitational potential energy. Since it has very high gravitational potential energy, it implies kinetic energy is low. Now, kinetic energy is equals to half mv squared. So if it's low, it means it's moving slowly here. Now at B, it's very close to the sun, meaning the height is smaller. Therefore, most of the gravitational potential energy has been converted to kinetic energy. So it has very low gravitational potential energy. Where is the gravitational potential energy going? It has been converted to kinetic energy. So it has very high kinetic energy. Since kinetic energy determines the speed, so it should be moving faster. This is another route you can take. So we have two ways to get the second mark. I use the gravitational pull. You can use energy conversions. With this, you now get out of 2 out of 2. Because there are two command words. Describe, I've described in my first point. Explain, I explained in my second point. For me to earn these 2 marks. Part C says, at one position in its orbit, the comet is 6.6 times 10 to the power negative 6 light years away from the Earth. State the meaning of the term light year. So you should know that light year is distance. Light year is distance. What distance moved by light in a vacuum of space within a year? When light is moving at its speed of 3.0 times 10 to the power 8 meters per second, and it continues to move within a year, the distance it covers is what we call a light year. So the simple definition which was expected of you was a light year is the distance that light travels in 1 year. Part 2 of item C says, determine the distance in meters between the comet and the Earth. So we are given the distance in light years. They want it in meters. So let's start by extracting data. What are we given? We are given distance in light years. So the distance in light year is 6.6 times 10 to the power negative 6 light years. We are also supposed to know 1 light year from this definition. A light year is equivalent to 9.5 times 10 to the power 15 meters. How do we get to this number? We said 1 light year is equals to distance. Which distance? Moved by light at its speed within a period of 1 year. And we know that distance is speed times time. So what is the speed of light? 3.0 times 10 to the power 8 meters per second times time. What time? 1 year. The distance traveled by light within a period of 1 year. So for us to get 9.5 times 10 to the power 15, we do our 3.0 times 10 to the power 8 meters per second times 1 year is the same as 365 days. In 365 days, we have 24 hours. In each hour, we have 60 minutes. In each minute, we have 60 seconds. So this is the time we call 1 light year. So we can safely say 1 light year is equals to 9.5 times 10 to the power 15 meters from this product. Take note, your time must be in seconds because the speed of light is in meters per second. Once this is found, then we say number of light years times the distance in a light year. So let's recall the equation. Distance is equal to number of light years separating 2 points times distance in 1 light year. By substitution, we have number of light years 6.6 times 10 to the power negative 6, and in 1 light year we have 9.5 times 10 to the power 15, giving us a total distance of 6.3 times 10 to the power 10 meters. We have reached the end of our walkthrough. I hope you have been helped and you have been enriched in revising the October-November 2025 component 41 of your IGCSE Physics. Hoping to see you in our next walkthrough. If you have not subscribed to this channel, ensure you hit the subscribe button and the notification bell so that you don't miss our next walkthrough.